This lecture is called Around and Around We Go, and it says, Do not disturb my circles. Those were Archimedes' last words. Archimedes is a famous scientist who was actually killed by a Roman soldier while he was investigating some physics phenomena. So his famous last words is, Do not disturb my circle. So, with that in mind, let's take a look at the learning goals for this. And the first one is we want you to be able to describe speed, velocity, acceleration, and force in terms of circular motion. It's just slightly different than projectiles and slightly different from linear motion, and we need to be able to show the difference between those. We want to be able to calculate the tangential velocity and the centripetal acceleration, as well as the centripetal force for objects in circular motion. And we want to be able to relate what we learned in circular motion to how it compares to kinematics and how it relates to dynamics as well, which was our study of force. So the first thing we want to do is we want to look at the idea of projectiles. And the idea of projectiles basically said that if you fire a projectile fast enough, it won't ever hit the ground. Instead, what it'll do is it'll achieve an orbit around the Earth and it will keep going in circular motion. So we can see that again. If you fire it fast enough, okay, that parabolic path actually extends where it goes in a complete circular motion around the Earth. So that's what would happen if you shot a bird fast enough where the curve of the Earth actually mattered. Too slow, you can see that the curve of the Earth isn't sufficient for it to achieve a stable orbit. Instead, it crashes into the surface of the Earth, and basically what you have there is projectile motion. It takes a parabolic path and ends up striking the ground. Now, if you fire a projectile too fast, like you'll see in this next example, you will see that it also does not achieve a stable circular motion. Instead, it goes off, may come back on the screen after a little while, but basically it achieves what we call escape velocity. So in order to achieve stable circular motion, you have to have the just right speed. Velocity in circular motion is very similar to that in linear motion, but remember, we have to re-examine some of our variables. So the equation that we have for velocity is generally velocity is equal to the displacement divided by the time. Now the problem with that is when you look at a circle and you go around the circle once, technically your displacement is zero, but that doesn't mean that you have zero velocity. So we really need to re-examine this. And what we do whenever we look at velocity in circular motion, we actually use this outside part of the circle. Now you learned this in geometry was the term circumference. So you have velocity is equal to the delta d is replaced by the term 2 pi r. Okay, so that's the equation that we have for the circumference, or pi d, however you want to remember it. But 2 pi r, and then we divide it by, instead of referencing delta t, because delta t can reference any time, 1, 2, 3, 4, 5 seconds, what we do is we emphasize it with a capital T. And that actually refers to the period, or the time that it takes to go around the circle one time. So it's very, very similar. It's almost the same thing, but there's just a couple of modifications that we need to do here. So if we take a closer look at the velocity, the objects are always changing direction. So even though an object in what's called uniform circular motion is where the object is always the same speed as it goes around the circle. So for example, it's always 10 meters per second. But even if it's always 10 meters per second, even if the speed is always constant, the velocity is always different, because remember, velocity includes both magnitude and direction. And if you look at any given point, the direction of the velocity is changing as you make your way around the circular path. Velocity is referenced as vt. So if we go back up to our formula, it really is v and then a little subscript t. And the reason for that is that indicates the direction of the velocity. Velocity is tangent to the circle. So if you draw any point on the circle, the velocity is tangent to that point. So the objects move in circular speed. They have a constant speed, but they're still accelerating because they have this change in direction. So let's take a look at a couple of examples. The first one we have is we have an athlete that is participating in the hammer throw. And if you look at the hammer throw, it says it gives us a velocity of 10 meters per second. And then it actually gives us two lengths. And if you were to look at this right here is our center point of turning in a circle. So if you look, his arms contribute partly to the radius, but the radius plus the length of his arms plus the length of the chain actually represent the radius. So if we look at our given variables, we have the tangential velocity, and that's 10 meters per second. we have the radius is going to be 2.9 meters, which is what we get when we add these two distance terms together. And then you also have we're trying to solve for the period, how long it takes for him to rotate around once. So we look at the equation Vt equals 2 pi r over t, and the reason why we know that is because he's turning in circular motion. So we say 10 equals 2 pi times 2.9 over t. Multiply both sides by t, divide both sides by 10, and when we do that, what we're left with is now t equals 2 pi times 2.9 divided by 10. And when you multiply that all out on your calculator, you should get something around 1.82 seconds. In the next example, we're looking at a circular saw. And it says, what is the velocity of a circular saw in diameter that completes 200 rotations every second? And a lot of people look at this and they get kind of confused with this idea of 200 rotations per second. What that represents is that's an angular velocity. So that's actually pretty close to what we want. What it's saying is you have 200 rotations per second. So if I could figure out how to relate rotations to meters, then this is just a straight conversion problem. So if I look at a circular motion, when something right here rotates one time, you should realize that that is the circumference. So one rotation in this case is equal to 2 pi r, or since we don't want to put a formula in our conversion, we would say 2 pi times 0.4. When we multiply this out now, we're not in rotations anymore. Since this was in meters, we're now in meters. So now we have meters over seconds, which is the term for velocity. So when you multiply this all out, you should end up with a value of 251 meters per second. Alright, this is an interesting example because you're trying to figure out how fast the Earth moves. Now, for some reason, a lot of people think that the Earth doesn't move because they can't feel it. Remember, you can't feel velocity. It's the law of inertia. It's just the way it is. So you should be able to calculate using these big numbers here that the velocity of the Earth as it travels around the Sun is roughly 29,865 meters per second. So now we have this idea of changing velocity. So since we have this idea of changing velocity, so since the velocity is something here and then the velocity is something different here, even if they're the same number, because they change direction, any sort of change in velocity requires an acceleration. By definition, acceleration is the change in velocity. So if you were to take a look at this and kind of look at it geometrically speaking, you'll see that because of the change in direction, the acceleration is always directed towards the center. In fact, we call it the centripetal acceleration. That's an A and a sub C. Centripetal means that it's center seeking, so the acceleration is always trying to get towards the middle. So, if we look at the centripetal acceleration, this is our new formula. The centripetal acceleration is equal to the tangential velocity squared divided by the radius. So this new variable, it's an acceleration, so it's in meters per second squared, and it's still measured the same way. Tangential velocity is still a velocity, so it's still measured the same. The radius is a distance, so it's still measured the same. So these are really not new variables. We're just putting words in front of them to denote the direction in which they act. But they're the same things that we covered in the kinematics and even earlier this unit with projectiles. So we come to example B1. It says a CD has a diameter of 120 millimeters, and you should circle that and say, hey, there's something going on there. I gotta do something there. And then also it says it rotates at 480 rotations per second. What is the acceleration of a point on the edge of a CD? So we're trying to figure out what the acceleration is on the point of the edge of the CD. So the formula that we have is A equals Vt squared over R. In this case, we have the velocity in 480 rotations per second. So we're going to have to do something with that. So the first thing we want to do is we want to convert 480 rotations per second, and we want to go ahead and convert that into a value that we can deal with. So the first thing that we need to do is we need to set up our rotations to meters conversion. Remember, one rotation is equal to 2 pi r, Now in this case, we need to convert this R value first. 120 millimeter diameter would equal a 60 millimeter radius. And when you convert 60 millimeters to meters, this value becomes 0.06 meters. So now you take your calculator and you take 480 and you multiply it by 2 times pi times 0.06, and when you do that, you get a velocity of about 180 meters per second, 181 meters per second. Now remember, that's just the velocity. That's going to be this top squared term. So you'd say 181 squared. Now you have to take it and you have to divide it by the radius value. But remember, the radius value is not 120. We had to go ahead and divide that out. So just be aware of that whenever you're doing your calculations, that you need to make sure that number one, you square the velocity, and number two, that you're dividing by the radius and not by the diameter. So whenever you divide this out, you should end up getting an acceleration of approximately 545,600 meters per second squared, which is a heck of a lot of acceleration that makes that CD spin that fast. So now we look at example B2, and it says an athlete throws a discus rotating at 3 meters per second and accelerating at 8 meters per second squared. And what is the length of the athlete's arm? So this is a just straightforward application of our centripetal acceleration equation. You should be able to plug your numbers into the appropriate places and solve for the radius as 1.125 meters. This question is looking at a tether ball, and it says, okay, when the tether ball is fully extended and moving in a circular motion, it wants to know what the acceleration of that tether ball is when its 2.1 meters is fully extended. So the first thing you need to do is realize you got to calculate velocity, or you've got velocity and radius, and you plug it into the equation, and you should be able to get an acceleration of 68.6 meters per second squared. But there's a part two of this. It says in tethered ball, the length of the rope is always changing. So how does the acceleration change when the length of the rope changes? So let's examine the formula a little bit closer. Whenever you take a look at the formula, this radius term is in the denominator. But it's not quite that simple, because remember, in the velocity term, velocity also has the radius built into it. So it turns out that whenever you plug in these values, whenever you increase the radius, you actually increase the acceleration, even though it looks like it doesn't. And the reason for that is remember, this 2 pi r over t is a squared term. And what that does is it makes the top 4 pi squared r squared over t squared, and then you take that and divide it by the r value. So it turns out that the r cancels out of the denominator. So most people look at it and they go, oh, well, if you decrease the radius, you're going to increase the acceleration. That's not the case whenever you take a look at it and you expand the variables out. It turns out that when you increase the radius, you also increase the acceleration. Centripetal force. So because every acceleration requires a force, the centripetal acceleration is also going to require a centripetal force. The centripetal force is not another force. It is not something like the normal force or the gravitational force. It's not. It's merely a description of the net force that causes an object to move in a circle. The centripetal force can be caused by friction, it can be caused by gravity, it can be caused by the electrostatic force that we cover later, it can be caused by tension, the applied force, but it is not in and of itself a force. You need to keep that in mind. Centripetal force should never be drawn on a free body diagram. If you have a free body diagram, centripetal force should never be drawn on it, because the centripetal force is the net force. So, you can use the formula that we have as the Newton's second law, F equals ma. Well, the A here is going to be the centripetal acceleration. So it turns out that this is also going to be the centripetal force. So let's take an example. Let's take a look at an example. And the first one we have, it says, what is the centripetal force required to keep the Earth in orbit around the Sun if it completes one revolution per year at an average orbital distance of 1.5 times 10 to the 11th meters per second, or excuse me, meters? So now this question would take a while, except for the fact that in A3, we already calculated the velocity of Earth. We said it's 29,865 meters per second. So now that actually shortens our calculation quite a bit. We can use the velocity to calculate the acceleration by using v squared over r. So let's do that real quick. So we say, okay, 29,865 squared divided by the radius, which is 1.5 times 10 to the 11th, results in a really small acceleration. That really small acceleration is like 0.00595 meters per second squared. So you have a really, really small acceleration. And you may be expecting a really, really small force as well. But realize force is equal to mass times acceleration. Although the acceleration is really small, the mass is really, really large. So whenever you plug these values in, you get 5.98 times 10 to the 24th, a massive number, times 0.00595, pretty small number, but nowhere near as small as this one is large. When you multiply those out, you end up getting a number of 3.56 times 10 to the 22nd newtons, which incidentally is equal to the gravitational force if you were to calculate the gravitational force between the two objects that we will in Unit 5. So just keep that number in mind. Number C2 says an object that moves in counterclockwise circular motion. So that means it's moving this way. Okay, it wants us to draw the velocity, acceleration, and force vectors at point A. So at point A, remember, velocity is tangent to the circular path. So we know that it is this line right here. Now, we have to decide which way the arrow points, and the arrow will point in the direction that it was moving. So since when the object comes around to point A, it's moving in this direction, this is the direction that the arrow will go. So we can label that VT. Now remember, the acceleration and the force are both A sub c and F sub c. What that means is that they're directed towards the exact center of the circular path. So this could be called FC and AC. It's the same vector. Just so you know, these two are perpendicular to each other. They're always at 90 degrees. And finally, the third example, you should be able to calculate that the force required to move a 10 kilogram object in a circle with an acceleration of 2, you can use Newton's second law, and you should be able to figure out that it is 20 newtons.